Good evening. I'm glad to open the autumn session of our seminar. And our first speaker is Professor Dmitry Talalaev, and he will speak about the category of braided sets, extensions, and two analogs. Yeah, please.
Thank you very much for invitation. I plan to talk about maybe very known things, but for me it's a new point of view on familiar things like Yang-Baxter equation and related algebraic structures.
А что ты говоришь на импортном языке? Никого ж нет?
The first object of my talk is the Yang-Baxter equation. Baxter equation. It's a theoretical equation. So it's a very known thing. 1, 2, 3, 3, like this. Rij is a map from x3 to x3, just the Cartesian third product of a set x. So these maps are just the copies of the same map of the map R, which is a map from the Cartesian square of the set X. And the next such map acts in components indicated.
Две функции от двух переменных.
Yes, we can think about it about these elements as two functions as two B operations. From the operatic point of view, R is an operation of biarity 2-2. Is a 2-2 biarity operation. So the role of this equation is very known. From my point of view, it's some structural equation which symbolize, I don't know, the action of the braid group on object, on vector spaces, on many different things. Biarность. Biarity. And I will call X with such R a Yang-Baxter set. Related structure is a solution of the braid relation. It's like this, braid relation. S is a map of the same nature, but the indices here are different, and really here it is really a representation of the braid group. So we can thought that X with such S is a map. Say it is a map from braid group to maps from xn to xn, which preserves the positions of the Cartesian products here. Okay, and such x with s is the braided set. Braided set.
What is the relation between that and
Relation. If we define an element P in maps from x cross x to x cross x, which is just a permutation. Then there is a theorem. If XR is the Yang-Baxter set, if and only if XPR is a braided set. Very known. So the subject of my talk is to consider such object as an object of some category. It means that to state the problems in a category about morphisms, about simple object, about exact sequences in a category, which from my technical motivation is a way to construct solutions for Yang-Baxter equation from simple one to more complicated ones. So it's some way to manage all the family of solutions of the Yang-Baxter equation. So the first question extensions of braided sets or Yang-Baxter sets. And there are some important examples of such extensions. But I will start from related algebraic structures. The structures related with the notion of a braided set. Algebraic structures. Self-distributive set. Is a set with operation subject to some axioms. First one. Like this. And the first exactly the property of self-distributivity. It is the following one: A, B, C, B, same as A, C, B. More exactly, here is I presented to you the axioms of the structure, which is called quandle. And the self-distributivity, it is only third axiom from this list.
Квады,
Quandle.
как это переводится?
Quandle.
А это значит такой же, как и здесь? Там
Yes.
непонятно, чего это
Yes,
значит.
it is a star, an operation. Is it known as a definition?
No.
Okay.
And
Example.
even, yeah.
Example. If G is a group, then G with operation star, there A star B is B minus 1 B is a quandle. Theorem. Let X star be, is it necessary to verify
No.
the self-distributivity?
Верим.
Okay. If X with an operation star is a self-distributive set, self-distributive set, then a map X, Y to X, X, Y is a braided set or Yan-Baxter set, but to be precise,
If you buy the structure, young box, then
yeah, yes. It is a braided set. So just by transposition, we can construct a solution of the Yan-Baxter equation. Yes.
Wait, so you mean R or PR?
Here is PR. So
PR,
it's better
okay.
to say that it is S.
Okay,
So it's a solution of the braid relation.
okay, thanks.
So it's an example of the solution for the Yan-Baxter for the braid relation and respectively for the Yan-Baxter equation, which came from the group theory. Okay, there is another interesting solution for the Yan-Baxter equation, also coming from the group theory. It is related with the notion skew brace. And X is a skew brace if it is equipped with two group operations such that X dot and X circle are groups. And the multiplications are agreed by the following equation. Like this.
B dot C, yes?
Yes, here is dot.
And
here is it inverse with respect to dot,
this,
and here it is dot.
an example.
example is related with the group of exact decomposition. Let G be a group of exact decomposition.
Скажи, пожалуйста. А что означает произведение без значка?
It's dot.
Точка.
And the inverse is also with respect to dot.
А вот этот кружок, это разные вещи?
It is dot. Circle, it's a different operation. G is a group of exact decomposition if G1, G2 are subgroups, and each element of group G has exactly one decomposition as a product G2, such that Gi is an element of a group Gi.
Ну, это example чего?
Just a moment. In this case, we can define two operations. The dot operation is just a multiplication in a group, and the circle multiplication is defined as follows. A, B is the following product. A1, it is the first element in the decomposition. B and A2. In another language, we can think that so it's related with the following problem, with the following construction. If an algebra G is a direct sum of its two subalgebras, one define just subalgebras, not ideals. One define what is called GDEq, which is the same thing as the linear space, but the product, the commutator is the commutator here minus commutator here, and they commute between them. G1 plus G2, H1 plus H2 is equal J1 H1 minus G2 H2. It is a known construction in the theory of quantum groups and Lie algebras, so in the core of this theory. But it was known.
It satisfies Jacobi, yes?
Yes.
Because they are subalgebra.
Yes. So if we exponentiate this Lie bracket, it gives exactly this new product on the group, and they are related exactly by this relation.
Can you just finish the sentence? You said it was known before.
So I suppose that this construction was invented by algebraists, which didn't know the dressing transformation in quantum groups. So
just I know that the dressing transformation actually appears in work of Ilford.
So I have intuition that both directions came from different subjects. I explained this construction for the reason that we can construct solution for the Yang-Baxter equation starting from this object. Generally, if we have a skew brace, we can construct such a map R G from A, B. B minus 1 A B there lambda lambda A B is A minus 1 A B. Okay, so the statement is that R like this. It is a solution of the Yang-Baxter equation. R G A B, a solution for Yang-Baxter equation.
So any
For any skew brace,
defines
yes.
such solution.
So the first application.
Я прослушал, что это лямбда.
So for the skew brace produced by the group of exact decomposition, it is the following thing. B A2 minus 1 A1 minus 1, and here there's just the multiplication in the group A1 B A2. So it is a conjugation by a part of an element A. Demand, you know what does it mean? It comes from the by cross product of two groups. So then you pass one element from another, you apply all the partial conjugation. So it is
It's drifting. It's drifting.
yes. Mm-hmm. Okay. So my purpose is to define some extensions of solutions of Yang-Baxter equation. And the first one.
Sorry, can I just ask you? RG is a map from two copies of G to
Yes. To copies of G.
it's a
Yeah.
map from G10.
First
It's not in G10, it's in G like the algebra.
No, it's for the group.
G10.
Yes. So now extensions. So from the previous example, then from group we constructed a quandle.
Silly question. Can it be explained why such constructions provide limited solutions? Because it is not obvious. How can one guess that such constructions are useful to solve Yang-Baxter?
So principally, it explains how we commute two elements like this, A and B in a group. And we apply the operations. So it's an element A1, A2, B1, B2. And we try to transpose this from one to another and explain some local expression like lambda. So we express a result in the same way as a product of two subgroups. And just this simple parameterization of a group produce a solution of the Yang-Baxter equation in coordinates, if you want. So the nature of the Yang-Baxter equation is the action of the braid group. And you transpose some elements in some coordinates, in some context.
Те решения Yang-Baxter это тяжелое, а вот это вот найти, что легко найти, а из чего уже потом строить.
It's not a very simple problem to find a group with a direct with an exact decomposition. So no,
Что еще раз?
a group with an exact decomposition. So it's quite strict object. Okay, so the first idea to construct extension is to look for the extensions of groups. We can consider extensions of groups, produce.
Вообще вот эта вот алгебраическая структура эквивалентна той групповой или как?
Yes.
А?
Yes. Lie algebraic structure. Yes. Yes. It is equivalent to this one because it is a product.
Ну, вообще-то у тебя вот эта алгебраическая структура почти прямая сумма. Вот замени минус на плюс, и все, будет прямая сумма.
It is also quite a direct product, but with an inverse multiplication on the second component. A1, A2, we multiply by B1, B2. If you want, we state here the comma. And it is the following thing. It is A1, B1. B2, A2.
Вот в конструкции тройки Манина там все-таки есть две подарки.
Do you understand that it's the same thing? This one and this one. So we now parameterize element of the group by pairs. A1 from G1, A2 from G2. We multiply pairs by this rule. So
I'm sure that this is the same as in drink.
yes,
That he knows this. He spoke about it
yes.
yesterday. I wasn't installed yesterday.
I'm sure, but it's explained in different terms. Okay. So from this exact sequence of group, we can construct an exact sequence of quandles of self-distributive sets. I will write the same thing, but I will think about this as an exact sequence of self-distributive sets. From these sets, I can construct solutions from the Yang-Baxter equation, and the construction here, RGK, is meant as an extensions of solutions of Yang-Baxter equation from the body terms. And I will explain this construction in more details.
Еще раз. Это что? Extension?
Extension of groups.
Какой?
Some extension. I will talk about central extensions. K is GK central extension. So I think I need the K to be commutative. Okay.
But in principle, you can take another degree.
Yes. I'd like to explain the construction of solutions for the parametric Yang-Baxter equation, which is interpreted as an extension of corresponding groups. So we consider central extension with commutative K, and I will parameterize element of GK by pairs J and A, such that there's an element from J, there's an element from K, and the product in the group is some element J A H B. It is an element J with parameters N B with H, and here it is a commutative multiplication. From this multiplication in the group GK, I can construct an operation star in the corresponding self-distributive set. So it's a conjugation.
What is GEB?
GEHAB. It's some operation which depends on A and B.
Что такое за операция M?
Multiplication in the central extension here can be expressed in, if you want, in coordinates. I explained just the simple thing that the projection of this multiplication to K is AB.
Ты можешь объяснить, что является генеральной целью? Вот, Нет, ну вот есть последовательность некоторых конструкций. Значит, ты объясняешь, как из простых объектов поставить более сложные. Ну вот, например, вот этого, да, существует вот такое разложение. Меня вполне устроит. Вот ты, пожалуйста, сказал.
It's a different idea how to construct solution for the Yang-Baxter equation from different structures. But if you want to describe all solution of the Yang-Baxter equation.
Но сам по себе Yang-Baxter equation интересен с точки зрения приложения. Но в обычном сеттинге, как там интегрируемые системы, там то все, здесь это все тоже есть или нет? Можно ли там строить подалку в рубе, так сказать, что-нибудь?
For the moment, it is distant from the integrable system motivation.
То есть здесь этого нет.
No.
А что здесь есть?
How to construct new solution of the Yang-Baxter equation?
Способы, как построить приложение. Вопрос нет.
Can we continue? So if we parameterize points of the extension of the central extension by pairs, the multiplication in GK is something like this. It means that the star operation in the associated quandle it is some section, if you want, some section of this extension. In these terms, the star operation J A star H B something like this. J star also with parameters A B with H, and here it is just A. Because it is a commutative group and the conjugation, the star, it is defined as conjugation of A with the help of B, so it is just A. So it is a self-distributive set, and with the help of this set, we can construct R A B from G to H, which is G H star A B G.
G is in G or in GK?
I'm sorry. It is from G. Theorem. R A B constructed from this set of data is a solution for the parametric Yen-Baxter equation, which is the following one: R AB 1, 2, C 1, 3, BC 2, 3 is equal to the same thing in inverse order.
This thing is a semi-direct product, isn't it? That formula, but the line above is a semi-direct product.
Here,
That, with this one here, the definition of RAB, semi-direct product of G, comma E with E, comma H. If you define this, if you define the action, you could write that formula in terms of a semi-direct product.
yes, surely. Yes.
That probably makes this
Mhm.
really obvious.
But it's known in theory of integrable systems. That's why it is important to make this relation. But it is naturally an extension of the solution of the Yen-Baxter equation. So from the group G, we obtain one solution for the Yen-Baxter equation, and this extension produces another solution of the Yen-Baxter equation on the bigger set, which is in fact the direct product, exactly the direct product of J multiplied by K. I'd like to present you an example of such construction.
Solution to the parametric Yen-Baxter equation is not a solution to the simple.
We can
We can
interpret it as,
use
yes.
this one.
Yeah. In traditional situation, the parameters are elements of some abelian group, for example, of the real numbers or complex numbers. And this map can be considered A B is a map from X to R. With trivial action on R, but it's naturally an extension because this this additional parameter, it acts on the rest on X. The simple example of this construction. So if we consider G just the unipotent subgroup in SL2 C SL2C the B plus, and here the factor group, the quotient group is SL2, just the Cartan part of this group. So it's an exact sequence of groups, and it produces the following solution for the parametric Yen-Baxter equation.
Sorry, what's the first term in the sequence? Is one mapped to which? The first term in the sequence.
Here, it is unipotent.
Element.
No. It's a group of high upper triangular matrices with unities on the diagonal.
So it's a subgroup, you've written element.
Of element like this.
That's an element.
No, it's a subgroup of unipotent.
No, but it's a misprint on the blackboard. That's what it's an element of.
Yeah.
I mean, I was really confused.
No. You're right. That's correct. So it's a subgroup of element like this. It is subgroup of elements B0 lambda minus 1. And it is subgroup of diagonal elements.
Там, конечно, у тебя там как-то был.
SL2C intersection with H with Cartan subgroup. Example. So it is explained in terms of parameters x, y are parameters from here, x is a of one element, y is a of different element. It is given by the formula x plus a squared.
So X and Y, they correspond to what we've written called A on the line.
Yes,
group.
yes.
Yeah.
It's better to write here x.
Yeah.
Mhm. And b is this element.
What about the next one, where it's lambda and lambda?
A
inverse?
and b are element.
Where it's written lambda and lambda inverse, should that B be a Y as well, or is it?
It is a complicated structure, and parameterization of this one are a and b.
But the other one is definitely A.
Yes, yes. B square. Y. Okay, it's like this. So this solution was known from different construction, but it can be obtained from this idea of extensions of group and extension of corresponding braided sets. Okay.
Почему так надо писать А в квадрате на Y, но Б в квадрате на Y?
Just the parameterization. It's not important.
Would you be able to write down what is MAB of GH here? Is it easy to take a long time?
No. It's
What is MAB in this case?
So it's explained how you commute this element, how this element acts on this. So I suppose it's x multiplied by the difference of mu and mu minus 1. Okay, so in fact I have two different construction of extensions, which has from my point of view some conceptual meaning. But maybe it's better to go to the next dimension. How do you think? Okay, I think it's more interesting to explain these constructions. So there is a complex which is related, a complex which calculates some cohomologies related to solutions of Yang-Baxter equation. It is called Yang-Baxter complex. But it is quite difficult to explain it in details. I just present you what is two cocycle for the Yang-Baxter complex. It means that there is a Yang-Baxter set X with the solution of the Yang-Baxter equation on the set X. And with this data, we associate some Yang-Baxter complex, and its cohomologies control some properties of this solution of the Yang-Baxter equation. So it is a cube with two ways to go through its two faces. I will denote the first the initial edges of this cube by x, y, and z. And the process of coloring of one edges is through two faces. and the solution of the Yang-Baxter equation is associated to two-phase. It means that X is R from X, Y. With this cube, we can associate two coloring processes from the from two parts of this cube, like this. Prime. Then we can color edges for the face Z and X, Z prime, X to prime, and the last thing is to color faces Z to prime, Y to prime, and it is only the one part of the cube. If we associate numbers 1, 2, 3.
You consider the pairs XR where R is the solution, yes?
R is the solution.
R is solution.
Yes.
R is-
Yes. So this part of coloring is associated with one part of the Yang-Baxter equation, and in this case, it is R12. And here was R13, 2, 3. So in a sense, it is a way to color these one edges, starting from the initial edges. But if we go through the different side of the two cube, we obtain an inverse composition of R, A two-cycle for the Yang-Baxter complex is defined as a function from x to the field K, such that phi x y x prime z phi prime z prime is equal to the product from the different side phi phi x z to prime phi phi x. The tilde are the colors which we obtain going through the different side.
Right. Like X prime, Y prime is R of X, Y. Can you write down what is X, Y, X tilde and Y tilde?
Sorry,
Can you
what?
write down what is X tilde and Y tilde?
What?
Like X prime, Y prime is R of X, Y.
Yes,
That's
yes.
Right. What is X prime, X tilde and Y tilde?
R from YZ
Yeah.
is Y tilde Z tilde.
Right.
But in this expression, it is this map. So it is applied in a different way.
1, 3.
Yeah.
What is K?
K is the field. C.
But when you apply R, that's when you apply R23 to X, Y, Z, you get Y to X, comma,
Yes.
Y tilde, Z
Yes.
tilde. Then when you apply R13,
Yes,
then you're going to get X tilde,
but we apply it to X
yeah,
and
and to Z tilde.
To
So
Z
you're going to
tilde.
get X tilde, comma, Y tilde, comma, Z tilde.
yes.
Just
But-
understand your notation.
But the Yang-Baxter equation means that X 2 prime, Y 2 prime, Z 2 prime is equal to X 2 tilde,
Yes, yes.
Z 2 tilde. But the partial colors in this process are important to define a good version of the Tuka cycle of the Yang-Baxter complex. So it's a definition.
Why only two cocycle and where is the differential?
Two cocycle because it is a function of two arguments.
Yes, but why you define only two cocycles?
They are important in the construction which I'm going to present. But there is all cocycles of.
But the theory is general.
Yes.
What is the length of the cocycles?
No, it's infinite. Infinite. Theorem. Let X R is the set theoretic is the Jan-Baxter set. Jan-Baxter set. It means that R is a solution of the Jan-Baxter equation. Let for the moment X be finite set. I suppose it's not very important, but it is simpler in my construction. Let associate a vector space with the set X such that it is just C. So okay, it's a vector space associated with X with basis A X in X. So for each element of the set X, I associate an element of the basis in the set V, in the space V. Then I define R like this. It is now a linear operator from Vx, Vx, and it is defined like as follows. I define it on basis elements Ax, Ay. It is phi y e x prime e y prime, such that x prime y prime is R of x and y.
And phi is our cocycle.
Yes, is a two cocycle. Then R is a solution of the vector Jan-Baxter equation. Solution for the vector Jan-Baxter equation. So it's a map in a tensor product. So we can write something in a tensor product of three.
Crystal can be done for three modules, yes?
Yes.
Essentially.
Yes, I suppose. Yes.
Mhm.
From my point of view, it's an analog of the central extension of groups. But now for the general, more general class of solution of the Jan-Baxter equation, is also defined with some.
So if X is a group, what's an example of P? In the case, because you just previously you showed us what happened with groups. If you said X is a group, can you give us an example of P?
Yes, but you mean an example of the cocycle of the Jan-Baxter of solution of the Jan-Baxter equation, which I'm not sure that it is the same as the group cocycles.
But what about if it's a essential extension case?
I could no. So all the calculations are complicated. But yes,
but not for the groups.
For the cocycles, I know some cocycles for. So in fact, I know cocycles for solution of the higher analog of the Jan-Baxter equation, for the Zamolodchikov equation. For some particular solutions of the Zamolodchikov equation, I know examples of three cocycles, which plays the same role in the theory of Zamolodchikov. It was not the point of my principle.
I'm just wondering what's the motivation for this condition. It's not obvious to me why I call it because what problem does it have?
for this reason. Yes. Okay.
Дим,
Да.
еще сколько?
Как скажете.
Ну, ты хочешь, может сказать, до утра, если мы скажем до утра.
Да?
Я никто не держит.
Ну вот я хочу сказать, если 5 минут, я подожду. Если...
I could explain you the plan.
Better not to be in a hurry. Well, we would like.
So I have another example of extensions. So principally, it is known. It is the same thing as derivative double.
But well, to come back to this cohomological theory. So you just for any Young-Baxter solution, we can construct such a cocycle.
Yes.
And
because we have got
the general construction of the complex
exactly
is complicated.
The complex of
Yes.
Young-Baxter. No, it is not
Maybe
very complex.
you say several ways to understand how it works, how we construct it.
Okay.
Without details, but
So
just to see.
the points in the plan. Description of Young-Baxter complex. Baxter complex. In fact, and simplex complex. I think it's 20 minutes. Another example of extensions, which works in the following context. We have two A and B are quasi-triangular Hopf algebras. So they.
Explanation.
Sorry?
It needs an explanation.
Okay, so quasi-triangular Hopf algebras, and we explain how to construct a new quasi-triangular Hopf algebra on the tensor product of A and B. So it is explained by some algebraic equation, which I'd like to express then also in some cohomological terms. So description of extension in algebraic by some algebraic relation.
So it also involves Young-Baxter. So A and B have to have an R.
Yes, the quasi-Hopf. Yes.
Quasi-Hopf involves
Algebraic relations. So some speculative point in my talk was planned in the context of category of tangles. Tangle, it's a bordism between points, and one of the relation of morphisms in tangles, it's a Young-Baxter equation.
What's a tangle?
Tangle is a bordism between set of points. And one of these bordisms is a tangle like this. So a natural relation in morphisms in the category of tangles is the Young-Baxter relation. So if we study functors from tangles to sets, it is related with the problem of classification of solution of Young-Baxter relations. Ну, это дальше спекуляция, так что ты ничего не потеряешь.
Сколько ты сейчас собираешься говорить?
Ну, давайте.
Мы сейчас голосуем.
Here it's 15 minutes. Here is 2 minutes.
Мне завтра очень рано вставать. Ладно, давай.
But this interpretation for me is important to generalize the problem of classification of the Yang-Baxter relations, because
What do you mean by classification?
so this functor
Translate the word tangle to Russian. Just understand.
по-моему, это тенглы. Тенглы не переводится так и звучит. Тенгл. This category of functors from tangles to sets, it is closely related to the category of braided sets. Okay, so to classify braided sets, it's the same, principally the same things as to classify functors from tangles to sets.
Yes, but
I couldn't say more.
What do you mean by classification? With respect to what?
Extensions, simple objects, morphism between solution of Yang-Baxter sets. So this ensemble of questions is natural from the categorical point of view. And this interpretation is important to me just to state the problem of description of solutions for the Zamolodchik of tetrahedron equation. It is the higher analog of the Yang-Baxter equation. For this object, the classification, even the morphism between solutions, it's not a clear structure. So, but
in high dimensions.
In high dimensions.
So the Yang-Baxter is for a cube.
Yes.
And this is for
cube. For cube. The tetrahedron equation, it serves for the same problem of coloring of two faces of the 4 cube. But it also 2 minutes because it's speculative. But there is a category of 2 tangles, which could be think as a bordism between such objects. So it's some forms between one tangles and the relations on 2 morphism on in the category of 2 tangles. It involves the tetrahedron equation. So so here I have no results.
You just mentioned Dmitry before.
Okay.
There's another thing.
No. So it is not very constructive, but this analogy between 1 tangles and 2 tangles allows to state the problem of classification of solution of the tetrahedron equation in some topological terms. So here is 1 30 minutes, depending on but I'm very interested in the algebraic structure of the tetrahedron equation, of its analog, which is called the permutahedron equation, which is even more general and topologically motivated. So it serves exactly to describe the 2 category of braided tangles, 2 braided category of tangles. Okay. So, but here it mostly discussion, mostly the explanation of structure which could serve to describe the solution of the tetrahedron equation. What do you prefer?
Well, first of all, I prefer the homological part.
Okay.
And maybe item 2 also about And this will be sufficient. It's now.
Okay, maybe we can planify another meeting. We can postpone this discussion for the next time
Well, it is one of.
to make it clearly.
Yes, it may be a reasonable option. Yes.
Because it's a very simple, very beautiful combinatorics. I suppose
Well, I would like
it has many different applications.
to hear it in much more detail. So maybe we shall postpone it.
Yes.
For another talk.
Yes.
Okay.
Because
Yes.
I like very much this equation, and I'd like to explain
Okay.
what is.
Okay.
Uh-huh.
Okay. So we skip now the homology. Okay.
So a 2-minute chunks.
Okay, I'd like to explain you what is the permutahedron equation.
The most complicated thing on the board.
Yes. No. Okay, in the category of tangles, there are morphisms which are just generators of the braid group. Sigma I, sigma, with relations I plus 1, I sigma I plus 1, which is a braid relation in the origin of Yang-Baxter equation. And there is also the relation of long commutativity if minus j is greater than 1. The two braided.
We are speaking of tangles of natural length.
Yes, of ordinary tangles.
Mhm.
But the two category of braided sets. An example of this two category is the deformed category of one tangles. Their both properties are not exactly fulfilled. So there are two morphisms which relate parts of these relations. There is two morphism relating these parts, and there is another two morphisms from this one. Yes. So in the Kapranov-Voevodsky construction of the braided two category, there is a relation which is defined by permutahedron. I will try to draw it here. And there is something from the different point. And the relation is over the two morphisms in this category. I will write it in some different parameterization, but in inverse order. So it is called the permutahedron relation, it is related with this diagram of two morphisms in these two categories. And for example, for the case where S is an identical two morphism, this expression provides so this part is just the Zamolodchik of tetrahedron equation. Okay, but I think here it is the partial stop in my talk. It will be a great pleasure to continue this explanation later.
So T is a map from 3 copies of X to 3 copies of X.
Yes, yes.
S is a map from 2 copies of X to 2 copies of X.
And the right side of the tetrahedron equation is the same product, but related with the inverse tetrahedron. And the the cohomology theory is can be constructed to each solution of n-simplex equation. The tetrahedron equation is the 3-simplex equation. The n-Baxter equation is the 2-simplex equation. So there is a family of n-simplex equation, and to each of them one could construct the cohomology theory.
And why Zamolodchik was interested in this equation?
It was from physical motivation.
Yes, that's why I asked.
He constructed the 3-dimensional models of statistical physics. So this equation is a natural analog of the integrability condition for the model statistical mechanical model on 3-dimensional lattice.
Oh, also an interesting topic.
We finish.
This part.
Yes.
Yes, this part, I think,
Okay.
yes.
Okay.
What does this, you suppose that T can be factorized, that we made a group, instead of just, it's so like 2 objects instead of 3. In
Yes.
that case, does it become something
Yes.
well,
Yes. There is a very interesting example of solution of the tetrahedron equation. Let X be a Yan-Baxter set, and Y be just X. The second, the Cartesian, the square of X. Let's consider phi, which acts from Y to Y. The same thing. But here we remember that it is X by X by X by X by X. And let phi be R13, R25, R46. It is a solution of the tetrahedron equation on this set. But it is non-trivial
Are they all
Braid.
commute? R13,
No.
R25, and R46, they all commute.
Yes, but they do not commute between different.
No, I can imagine, but this
Mm,
is why
yes,
it can be
yes,
this
yes. But you see,
R13, and they all jump by
Mhm.
the same.
another solution of the tetrahedron equation. Um, each from are just the real numbers.
You mean
so now
X,
this
Y,
is
Z?
a three cocycle.
No, phi it is a map from real element.
Yeah.
Mm,
And X, Y, and Z are all pairs. This is the case when they're numbers.
do you know the solution? It is called the Lustig solution. Lustig. And it is related to parameterization of the positive upper triangular matrices. So it is a cluster transformation in this cluster variety.
It can be factorized.
No.
it can only be written-
No.
cannot be written products of
No.
the
It is principally like this. It is the basic transformation from between two charts.
X plus Z equals 0. Just
It makes sense for positive.
positive.
Yes. So it is a parameterization of a completely positive up triangular matrices. Up triangular matrix is 3 by 3. It is the only transformation between two charts, two cluster charts from this cluster variety. And it solves the tetrahedron equation.
With S equals the identity.
With?
With S equals the identity.
Yes.
Because the tetrahedron is
Yes.
S equals the identity.
Yes. So this is the tetrahedron equation. And this is permutohedron equation.
Mhm. So I think that this solution was found long before the theory of Young-Baxter
Yes.
equations.
There is deformation of this solution. And it is a star triangle transformation in electric networks. It was found in the middle of 19th century. But it was not known that it solves some equation like the tetrahedron equation. It is star triangle transformation in electrical networks. Do you know what is what?
Well, no, I was hoping to attend all of your lectures last year, and I was too.
If in electrical network we exchange such block by triangular
Just dual.
with some change of conductances of edges, then the electrical networks doesn't change, and the form of this dependence of change of conductances from this to this is after some change of variables, this solution of the tetrahedron equation.
choosing ordinary relation between one over R, one over R equals one over R plus one over R.
Mhm. Yes, yeah.
Mhm.
Can you tell me what's the relation? I'm sorry, because I don't know what's the relation of electrical schemes with blah, blah, blah.
But you see, this transformation, it describes a natural mutation in electrical networks.
Yeah.
And it solves the tetrahedron equation.
Yeah, that's
If
But-
you are setting up these 3 points, you don't see any difference between them.
Yes, yes, yes.
It's the same.
Mhm, mhm. Just not in this point. If you have some embedding of this part,
Into that.
it is the same behavior of an electrical network. So this mutation in electrical network is described by this rational transformation. It solves the tetrahedron equation. But this transformation is deformation of the Lustig transformation, which explains how mutate the coordinates on the positive upper triangular matrices.
But sorry, this is not symmetric, this relation, but this one is physically symmetric. It doesn't care.
Yes, there is some transformation with involution. So yes, if you are interested in, I could give you another talk about it. It is very interesting, very intriguing matter.
Well, you and Jorgen both talked about this.
Uh-huh.
The other stuff. It is very interesting.
Mhm.
It is very interesting.
Мгм. Ну что, еще какой сюжет рисуете? Еще один сюжет.
Еще какой-нибудь забавный сюжет?
На ваш выбор, и тогда мы закончим.
I can explain how this this solution is related with the parameterization of positive.
Окей.
And I was in this, I thought very much. So
Let's A be matrix ABC like this, and we ask for the totally positive up triangular matrices. It means that A, B, and C are positive, and also this minor is positive. A, C minus B is also positive. The natural question here is to describe the minimal sufficient subset of minors, the positivity of which guarantees the positivity of all minors. So it is a principal question in cluster algebras and totally positive matrices. And here, what is sufficient? What is sufficient is delta. I suppose that A, B, and delta is sufficient because C is delta plus B divided by A. So if A, B, and delta are positive, then C is also positive. If C, beta, and delta are positive, when A is also positive. But another way to describe two charts in this cluster variety is to consider the parameterization of this unipotent subgroup by the following by the product of one parameter subgroups. X. I suppose that this expression is given by this. Yeah.
Нет, сверху.
And we have another way to multiply these factors. Write only non-zero elements. The transformation from this set to this is given by this expression. Maybe Z is here. Maybe the difference is here. That Y and Z. Z prime, Y prime. So in fact, it's two ways to parameterize the positive cell in this unipotent subgroup, and the transformation from one to another is given by this transformation, and it is related to
this combination always makes delta.
this exactly not. It is related with the positivity is explained better with another parameterization like this one T S Y U like this, but we can write here the multiplication in different form. U prime S prime C prime. This is a now it is a positive parameterization. Yes, it is possible. It is positive. It is positive, and the transformation between this part of variables also solves the tetrahedron equation, and this could be expressed from this one. So naturally, the solutions of tetrahedron equation appears from some problem of three decomposition. Like here in this group, there is a decomposition of this element as a product of three one parameter subgroups. Да. Из этого тоже какое-то очень хорошее получается решение. Ну, я сейчас его не напишу сразу. Там, по-моему, не буду писать. Ну, в общем, тоже решение уровня интегрального.
Ну что, закончили?
Да.
Аппарат не нужен снова. Well, thanks a lot. Any questions, remarks?
I have questions, but it's very. May I ask you, My question is, I remember when I was in school, I remember that in electrical schemes, it was you could say you could change the graph of electrical scheme by. Can you recall me this?
Sub-triangle transformation.
Трехвершинный.
Звезда треугольник.
Да,
Звезда треугольник. Sub-triangle transformation.
Yes.
I written this transformation.
Okay. Okay. Thank you very much. Because it was this I remember from. Okay. So thank you.
Magically, this transformation solved the tetrahedron equation after some change of variables.
More questions? Then thanks a lot, and I hope that it is not the last talk of you
Me too.
at this seminar. Goodbye. So see you next Wednesday, same time.